Okay, we're going to try now, we're going to turn our chromosome on its side here. I'm going to draw it like this now. Alright, and we're going to keep on with our idea of crossing over and stuff, so keep all of that in mind. And keep in mind that our genes are on here. And keep in mind that there are these little perforations on here. Really bad at this. And that what happens with these perforations is that sometimes the crossing over occurs, sometimes it doesn't, but when it does, you can get the possibility of getting combinations that are not likely, let's say. So let's say let's stick with our model that we were talking about before. We're going to say that A, B, and E are normally on the chromosome together. That's the normal state. And that little a, little b, and little e are also, this would be kind of like you would say the normal state. But every now and then, when you breed flies, you find out you should always then get certain combinations. You should always get like, let's say, big A and big A. Then you should always get big B, big B. Those should always be there. And if you get little a, you're going to get little b. This is the easiest case. And let's say if you get big A, little a, you're going to get a big B, little b. Let's say that for survival reasons, you generally need to get this. And if you get anything other than this, then maybe you've had crossing over. There are probably easier ways. I'm going to do this with heterozygosity. This can be explained in other ways, but I'm going to make this is I guess this is the slightly harder case. But the idea is these should always go together. And if you get something different, if say you get an organism with big A, and then big B, little b, then you obviously have had crossing over. And what's causing that, they've exchanged a piece and you got a crossing over event over here. This is what you're expecting, one of these on one chromosome, one of these, but then you should also be expecting a big B over here and another big B, and you got a little b. So one of these, like this one, there was a crossing over event, and one of these two crossed over, and that happens a certain percentage of the time, and it happens on percentage of the time based on its location to the other one. In other words, if you're further away, all right, you're actually more likely to have a crossing over event. If you're close, all right, so if A is here and B is way over here, you have all these different perforations in here and all these potential possibilities for a crossing over event. But of course, if it never happens, well, you're probably really close. You're probably like right next to it. B would be right here. But it happens a little more often if you're here, or a little more often if you're here, or here, or here. And so the further away, the more often you would get the crossing over. So how far away you are can be measured by how many of these events occur. So if you end up with 5% of your flies with this case, that might be, maybe medium amount. And you can use this 5% to say, tell you that the distance compared to another fly, and another fly with another set of genes, maybe A and E. So you got big A, and big A, little e, and I'm sorry, big E, little e. Maybe you get this, And that happens, that happens 10% of the time. Well, that's telling you that this is twice as far away as this one. So this one is maybe certain, we're going to call them mapping units, and I'm going to show you the calculation a little bit. But what this is telling you is that because they were further away, this crossing over was more likely to occur. All right, so you got more flies of this odd type. All right, if there are fewer of this type, then this was closer, and you can use this as a measurement, the percentage of flies that you get as a measurement for the distance between these two alleles. So there are some alleles that we know where they are. So let's take a new gene, let's put it right here, and let's call that one Z. And Z, we know exactly where it is. It's at some location X, or we'll just make up a number here at, there was a way to say this, but you know, 2.7 or something. It's at this specific location. I'm just making something up here, right here. And we get these numbers and we check out Z, and what we are getting with Z, all right, with little e, all right, showing up or whatever, and it's happening a certain percentage of the time. And when you get that, and it says, oh, 7%, let's say, so that would be like 7 units. Well, here's the problem. You don't know which direction. So you don't know if it's down here by 7 or if it's up here by 7. We don't know if it's positive or negative 7. But there can be no 0. All right. So if your number is too large, if your distance is so large it makes it to 0, it can't be in that direction. And now you know, oh, well then I must be at about 9.7 over here. That's kind of the way you work these problems, and we'll go through this, but this is a kind of a graphic orientation that maybe will help you understand how mapping occurs and how it's related to this crossing over process. Now, I've given you a very general way of looking at it, probably not the I didn't give you the easiest method because I allowed multiple alleles, and so it works in with the way you've been taught genetics. Generally, you just learn this as A and B, and you don't worry about the fact that you've got 2 copies. I did just realize that that's actually how you have to do it when you get serious about this. But the idea here is, I hope you understand that along this single chromosome, you're going to have some crossing over, and when you find certain changes in the genotypes of your organism, and you calculate them, and you're getting these weird numbers that you shouldn't get. You're getting a certain number of this combination that should never exist if everything stayed on the same chromosome. Then you know that, well, things are moving to the other chromosome. You're having this crossing over event, and that's going to help you figure out the distance that these genes are away from each other. And if you have a marker gene that you know where it's at, then you can use that to calculate the distance from your unknown gene. So a lot of times you're doing this with a gene that you don't know. It's uncharacterized, and you don't know where it is. And so therefore you use this method to determine the distance from a known gene. All right.